Hello everybody. So today I will talk about the geospatial indexes. So yeah, as the system design practice. So I will talk about three geospatial indexes named QuadTree, R-tree, and GeoHash. So that being said, let me get started with the QuadTree. So firstly, before talking about this, I'd like to clarify why geospatial indexes are needed. So the typical use cases in the system designs are for the Tinder or Uber. So let's say in Tinder, um, let's say I'm in Los Angeles and I'm looking for a person who is maybe 30 miles, um, up to 30 miles away from me. So in that case, from my current latitude and longitude, I have to get the data, which is inside of the radius, 30 miles. And that's what I like to do with the geospatial indexes. And let's say I put the data, each data of the point as the latitude and longitude, and use the composite indexes for latitude and longitude. In that case, what happens is that from the current place, I'd like to get the, let's say, near person, the point which are near. So I can use the index for longitude only. For latitude, I cannot use the index. So what I mean to say is composite index doesn't work. So I will show it to you what I mean by that. So let's say I'm three. Okay, let's say I'm at point 5634, and I'm looking for the kind of um, I'm looking for point where, so this is, yeah, okay. So let's say I'd like to get all the point with this query. So if I create the composite index for x and y, internally data is stored in the B tree in this way. So let's say there's so many points, like 1, 1, and 1, 2, and then 2, 10, 3, 45. Okay, so let's say these are the points in the database. So if I create the composite index of x and y, I actually sorted already, but data is sorted in this way, sorted by the tuple, and then these points creates the B tree in this order. So what it means that I can, filter the range of x with this. So with this, where x is 55 to 57, I can filter with this. But inside of this data, it doesn't mean y is sorted, as you can see, because 5612 is actually later than 5545. So these y are not sorted. So what I mean is that I can, if I create the index with composite index, I can filter the point with only x. I cannot filter with xy. Yeah. Yeah. So, sorry, I'd like to be a bit more clear. So I can filter with x first, and I can get this range. But after that, I cannot filter with y because this composite index sorts the point in this way, but inside of the filtered X range, Y's are not sorted. So I cannot use the filtering with binary search anymore. Okay, so that's why we need the special indexes for geolocational searches. Simple XY, latitude, longitude, composite index doesn't work. Okay. So firstly, I will talk about the kind of tree-structured geospatial indexes. Yeah, to be honest, B3 is also actually tree structure, so it's a bit confusing maybe. So yeah, but let me go with this. So I will show the picture of quad trees. So my concern is the XY plane or longitude latitude plane, and there are so many points, and I like to filter the points with X range and Y range. So with this point, let's say for example, I'd like to filter the point in the some square like this, or maybe like this. I don't know. Yeah. So, and the question is how I can optimize this, how I can speed up the query. So, as I can see from here, yeah, I can use the tree structure. So, firstly, okay. Firstly, because there is only one point, let's say only A exists, then this node A is, this point can be stored in the node, only one node. Yeah. Oh, wait a minute. Maybe this is not a good example. I will use this one. Yeah. So if there is only A, I need only one node. But let's say there are so many nodes, A and then B and C and D. Let's say there are so many points which are, concentrating on specific small range, small area. In that case, I cannot put all the nodes in the single node, assuming that I will create the tree structure. So in that case, I'd like to split this area into two nodes. So now, originally, let's say, only one node was responsible for this area, but because there are so many points, one single node responsible for, this area, and then another this area, and another this area, which has 2 points. So in that way, dynamically, according to the density of the points, the tree index is updated. So this is the core idea of the QuadTree. I will repeat again. So according to the density of the points, the tree structure is dynamically rebuilt. And I'd like to emphasize that when I say rebuilding in the QuadTree, it is just splitting. So if there is a node, and if there are so many points in this node, maybe this one, I split the area and create the child nodes and split the points into these child nodes. It doesn't mean I recreate the whole tree. So if there are so many points, it is split, and recursively, so the depth of the tree becomes so, big. Yeah, and definitely that's the problem of this, quad tree. Okay, so this is not the balanced tree. Yeah, the dense area can have the very big depth. Yeah, so for example, I'm creating the map of the restaurants in America, and there are so many restaurants in the New York City, So in that case, for that New York City, the depth of the node is very big, which means that if I try to search the um, specific area, I mean restaurants in a specific area in New York City, the query has to go down to the, you know, reef of the tree. Yeah, maybe reef or, you know, close to the reef. So yeah, that's the problem. And also, maybe I will write it down. Okay, so I would say queries on the dense area is not performant. And I will talk about one more drawback of this QuadTree. So, as I said, yeah, it builds the tree structure. But let's say there is a restaurant which moves from one area to the other area. And let's say there are so many such restaurants. In that case, the tree structure should be completely updated. Maybe it was so deep here, but if there are so many restaurants going out of this area, maybe I have to merge the nodes, child nodes, into one parent node, and there is the child nodes. Yeah. So, I mean, the update query of the points is not performant. And because I talked about the example of the restaurants, it wasn't actually, or I should say, for the restaurant, it doesn't happen. But let's say, and I think for Tinder, it doesn't happen that much. But for the Uber, it happens a lot because drivers are moving around, yeah, all the time. So I would say update queries, or I should say not suitable for dynamic data. Update queries are not performant. Okay, this is the second pros of this approach. Okay, but to be honest, this QuadTree, I'd like to give a good point. This is intuitive and easy. Yeah, this is intuitive. So I think I can say this is quite intuitive that when there is so many points in specific area, we split the area into sub areas and put them in as the child nodes. This is quite intuitive data structure. So I can say this is one of the benefits of using this. But that being said, actually this is not used in the production systems that much. Yeah. As an example, this is used in the Google Map tiling, not the searching, but tiling, in my understanding. But yeah, actually this is not used so much in the production system. Yeah, but about the QuadTree. Okay, so now we'll talk about the second one, R-tree. So R-tree is looks similar, kind of, to the spatial tree, but there is a difference in the how the area is split into sub areas. So this is R-tree. So in case of the QuadTree, when there is a, how should I say, when there is a dense area, it will split into two. However, for the R-tree, it is split into multiple rectangulars, and those rectangulars can be, I mean, can have the overlaps. So let's look at this example. originally it was a big whole rectangle. But then, let's say there are so many points around here and also around here, and it will split into two. And in this case, this T and U has the overlap here. So why does it have the overlap? Let's say, okay, so maybe I should talk a little bit more about these rectangles. So, so what is this rectangle? So actually, this rectangle corresponds to kind of area. So let's say I'm creating the map of the, let's say, yeah, Japan maybe, or maybe America, and each of the area is a state. In that case, the shape of the state is not rectangular. And for the latest searches queries, I'd like to put the state, one state, inside of one box. Or at least I would like not, I don't accept that the state is split into two boxes. Because in that case, I have to take a look at two boxes. So that's something. So in the case of the map of America, each box completely wraps each state. Yeah. So if I do that, of course, it is possible that the rectangle overlaps. Yeah. On the edges. Yeah. But I accept it. And that being said, so if I'd like to search the restaurant in California or Arizona or Nevada states, let's say I search for these three boxes. So these boxes are, sustained as the tree structure like this. So yeah, with this, tree structure like this, I go down the tree. Oh, yeah, to reach CDE and find it. Finds the restaurants inside. In this way, I did have to go down until these three boxes and take a look at the restaurants inside. And the benefit of this is, obviously, as I explained, I could search with state. State is not the, area like latitude, longitude area. So when I say California state, Nevada state, and Arizona state, it cannot say like latitude in this range and longitude in this range. Yeah. It's a, kind of weird, form of, space. So with this R3, those are easily handled. So yeah, I will rephrase it and repeat again. So I can search the point in an area which is not a rectangle. Yeah. And very, efficiently. So that's the, strong point of this R3. So let me write it down. So, oh, and one more thing. So let's say there are so many restaurants added to this area. Let's say NPQ, which is T. So in this T area, firstly, there are many restaurants here and here. And in this case, first, T is split into two areas, N and P. And then, let's say there are more restaurants built, open in around this area. In this case, In case of the quad tree, P will split into two. And I said the tree's depth is become bigger and bigger, larger and larger. But in case of the R tree, instead of splitting P into the two child nodes, I put Q here. So it can overlap. So there is a kind of sibling node added here. So in this way, our tree can sustain the depth of the tree to be, stable. I don't say stable, but balanced. Yeah, our tree is a balanced tree compared with, you know, QuadTree. So I can say this problem doesn't occur in QuadTree. So I would say tree is balanced, so query performance is stable. Okay. But still, that being said, it is not good for dynamic data. So I will copy this one again. Because, yeah, of course, as I said, when there are more and more points, or I should say point that moved from this area to this area, I have to, reconstruct the tree, kind of rebalance the tree so that it becomes a stable tree. So not suitable for dynamic data, just by QuadTree. And as I said, the strongest point is, suitable, or I don't say suitable, can handle non-point queries. And I can say this non-point as the term polygon. Can the point with polygon. The polygon is, not rectangular area, like form of California state or the form of Japan, or something like that. Okay, so this is about the R tree. Okay, so now we talk about the last one, GeoHash. So this uses the B tree index, and this looks completely different from QuadTree or R tree. So I will search Google Images. Okay, so this is GeoHash. So as I can see, the first tree, I can say the whole map is mapped into one big zone, and recursively, that rectangle is split into the same size rectangles, recursively, and of course, if there's dense area, I split or just say, I divide each area into sub areas so that the number of points in that area, dense area, doesn't be so many. And I can say, so when I take a look at the number assigned to this, or I should say, number assigned to each, rectangle, it has the same prefix. So when I take a look at this, let's say this area, it all begins with 0. And when I take a look at this, they share the same prefix 1, 3. So the cross area shares same longer prefix number, or I should say digits. So cross, so that's the point. So what's the benefit of this? So it is I can store this number into the B tree. So when I take a look at this number is sorted in this way: 1 0 1 2 3, then 1 0 1 1 1 2 1 3, then go to here and 2 0 2 1 2 2 2 3. Yeah, as you can see. And let's say I'd like to search around this area, around this 33. And let's say I'd like to get the point, which is within, let's say 1,000 kilo from this area. Or maybe 500 kilo is better. I don't know. Yeah, but around this area. In that case, from firstly, I can guess the number assigned to that exact center point, like 33. And then, according to the length of the radius of the search, I can find all the points, all the areas which are around. So let's say 033 is the center point, and if I try to get around this size, I try to get 30 zeros. I can get the area numbers 30, 31, 120, and then 300. And the database, engine takes a look at these 9 areas. Of course, the size becomes bigger. It becomes more. Yeah. And again, as I said, it's inside of the B plus 3. So I store these numbers in the, quite ordinary, let's say PostgreSQL column, and then I build the B plus 3. And if I build the B plus 3, let's take a look at this area. 030, 031, 032, 033. They're in the, they're consecutive numbers. So these are, what should I say? These appear in the database consecutively. Pointing these 4 areas are consecutive in a row in the database column. Oh no, sorry, in the database B3 index. Oh, but maybe it doesn't matter that much. Sorry, maybe I'm a bit confused. Anyway, the point is from the center, I can get the center area, then I can get the surrounding areas, and I get 9 areas, number 9 areas. Then the database engine concurrently take a look at each area and then gets the point which meets the condition. Condition is like 100 kilometer from the, inside a 100 kilometer radius from the center point, search point. So that can be done quickly with this, GeoHash index. And of course, if I'd like to search the area inside of, let's say, California state, let's say California is here, and if the, area can be inside of 21 to 23, the database engine takes a look at the point in 21 area and 23 area. So that's what happens. Okay. So I come back to this and I write down the pros and cons. So firstly, I can say the tree is actually not tree. It creates a B plus tree. So I can say instead of this, I can use B tree And this B tree is very traditional and very stable. So I can say I can use the mature technology and of course if I'd like to implement it in the database, the application logic should calculate these numbers, and these numbers are called hash. And in case of the Redis, Redis does the hash calculation by itself. Okay, so this is the first pro. And the second one is, actually this is good at dynamic data. Yeah. Because when the point is moved, all I just have to do is move the hash value. Wait, no, what does it mean? So I can say, oh, sorry, I will be clear on the case of relational database. So in case of the Redis, when I put x and y, latitude, longitude, Redis internally calculates the GeoHash. But let's say I'd like to implement the GeoHash, or use the GeoHash with PostgreSQL. Yeah, of course PostgreSQL has the PostGIS extension, which is this R3. So actually I can use it, but let's assume that I'd like to use the GeoHash in PostgreSQL. In that case, I use 3 columns. Number 1, latitude column. Number 2, longitude column. And number 3, GeoHash column. And GeoHash column is calculated in the application layer, application code. And that GeoHash has the B tree index. So that's how I can filter the point with GeoHash using B tree. And then finally, the point in that GeoHash are checked one by one by database engine. Okay, so this is the second strong point of the GeoHash. Yeah. And actually there is one more point. I don't want to call it the cons, but actually there is a point named boundary problem. So this is something I have to handle. Yeah. So, but yeah. Of course, as I said, if I use a GeoHash, I don't have to take care of the boundary problem. When I use the B tree and implement by myself in the application layer, I have to consider that. So what's the boundary problem? Okay, so I will talk about the boundary problem of GeoHash. So let's say I'd like to search the data points, which are within 100 kilometers from the point inside of, some point inside of area E. Yeah. So in that case, I have to take a look at F and G and D2 if the point is around this area, or if the point is in the center of E and the distance, or I should say radius, is not so high, not so big, I can take a look at only E. And if the point is around here, maybe I have to take a look at E and S, 2 areas. So this is a boundary problem. If the search point, center point, is close to the boundary, database engine may have to take a look at the adjacent areas too. And of course, for query for these multiple areas, database engine take a look in in a concurrent way if possible, and merge the result together. So that's about the boundary problem. Yeah. Okay. Actually, not so big problem, quite trivial, but still I have to take care of this. Okay, so that's pretty much it. Let me quickly review what I talked. So I talked about the geospatial indexes and the, biggest use case of geospatial indexes is, let's say, there is a point and I try to get other data point which is within specific distance from that point in radius. Yeah. And to efficiently return the result of this query, I have to use the geospatial indexes. And in geospatial indexes, I introduced 3 algorithms, or I should say data structures. Number 1 is QuadTree, which is literally tree structure, and for dense areas, the area is divided into sub areas, and other new child nodes are created. For R3, the area is divided into boxes, and boxes can have overlaps. Yeah, and boxes can, the benefit of using boxes is, let's say I try to search the point in California state. That California state is not the rectangle, but with R3, I can use a kind of rectangle which completely covers the California state shape. So that's a benefit. And for B3, GeoHash, what it does is from the latitude, longitude data or XY data, I create the hash value and put that hash value into the column in case of I use a relational database and creates a B3 index. And with that B3 index, I can find the area I have to take a look so quickly. Sorry. A database engine can filter the areas which it has to, scan very effectively. Okay, so those are the, 3 geospatial indexes. And let's say I'd like to use Uber. I will go with single key, GeoHash, because Uber drivers move around the areas. So, it's very dynamic, I can say. And also for Tinder, actually, Tinder is, in the case of Tinder, I talked that the recommendation is calculated in a daily cron job. So actually, it can take more time to query the data. So to be honest, I think it doesn't have the strict requirement. Yeah. But yeah, I think I can simply use a GeoHash maybe. Or maybe I can just use the PostGIS extension or PostgreSQL. In that case, I'm using the R3. So both of them are fine, I think. And let's say I'm using the I'm developing the Yelp, and Yelp has restaurants, and I try to search the restaurant with the kind of area name, right? California, or I should say Santa Monica. In that case, I would go with the R3. because what I like to do is the search with the polygon. And yeah, actually, I talked about the very simple case, like California state, but this polygon can be very, complex shape. Yeah, so I'll choose the R3 for Yelp. And of course, for Yelp restaurants, the data is not so dynamic. Restaurant doesn't move so often. So in that sense, R3 works fine. Okay, that being said, I finished my today's explanation on geospatial indexes. Thank you so much. Bye.